This is the supplementary video for Lecture 17, where we will solve the following problems in exercise 13. We will solve number 6, number 8, and number 20, 21, 22, and also we should solve the additional problem 2. So there are still 3 leftover problems, namely 28, 29, and the additional problem 1. So I will explain these problems during the lecture because they are very important and they might appear in the upcoming test. Let's start with number 20. So for number 20, we are asked to show the equation x to the cube plus e to the x equals to 0. We want to show this equation has exactly one real root. Okay, remember what we have learned in the section of continuity. We learned the intermediate value theorem. So which basically says if f is continuous on the closed interval AB, and moreover f of A does not equals to f of B, then for every number L sitting between A and f of A and FB, so they resist a C in the open interval AB such that f of C equals to L. So that's what the intermediate value theorem tells us. So we will use intermediate value theorem to locate one real root. But then we will need to use the mean value theorem to show that there resist exactly one real root. There won't be a second one. Okay, let's actually start with the solution. So we will start by setting f of x to be x cubed plus e to the x. Okay, so this is a polynomial function plus an exponential function. So therefore, we see that then f of x is continuous everywhere. So in the test, if you are asked with such a problem, so please make sure you declare the continuity before you invoke the intermediate value theorem. If you do not declare the continuity, so you will probably get 1 point off. Okay, so now let's actually try some special values. So for example, if f of 0, so this guy is going to be 0 plus e to the 0, and we see that this is going to give us 0 plus 1, which is going to be 1. Okay, so we are looking for one real root, and in order to use the intermediate value theorem, I need to have some x where the function takes a negative number. So in order to get the negative number, so it's necessary for us to choose x less than 0, because if x is greater than 0, so this guy is positive and e to the x is always positive. So what we will get is a positive number, and it won't be making a negative number for us to use. All right, so but the simplest negative number for us to use is simply x equals to -1. So we could try f of -1 and see what we have. So we get -1 to the cube plus e to the -1 power. So this will be -1 plus 1 over e. Well, 1 over e will be 1 over 2.7 or 1/8, etc. And this is going to be a number strictly less than 1. So a number strictly less than 1 together with the -1 will give us a negative number. So this way, we see that f of 0 is greater than 0, but f of -1 is less than 0. So that intermediate value theorem implies that there exists some number c between -1 and 0, such that f of c equals to 0. In other words, c cubed plus e to the c equals to 0. Therefore, we located one real root, namely c over here. So this part solves the problem that there exists a root. Okay, so in order to argue that there cannot be a second root, and we will have to use mean value theorem, but for this case, we only need to use the Rolle's theorem, the simple case. Okay, let's see what we have. Suppose there is another root, and let me just call it to be C1. that is not equals to C. So this basically means f of C1 equals to f of C equals to 0. But moreover, this C1 is not going to be equals to C. All right, so now look at my function over here. So my function is a polynomial function plus the exponential function. So this way we see that f is differentiable everywhere. So in particular, it is differentiable on the interval with endpoint C and C1. So I will avoid writing C comma C1 because I don't really know if C is less than C1. And similarly, I will avoid writing C1 comma C. So although I know this must be the only two cases, but then I find it easier to directly say that the function is differentiable on the interval with the endpoints C and C1. So this will unify these two different cases. Okay, so then we can apply the Rolle's theorem. Okay, so why can we use Rolle's theorem? So first, f of x is continuous everywhere. In particular, it's continuous on the closed interval with the endpoints C and C1. And moreover, we have also checked that it's differentiable on the open interval with the endpoints C and C1. So, and finally, we have got f of C1 equals to f of C equals to 0. So this is telling me that the Rolle's theorem can apply. Okay, what does Rolle's theorem tell us? Rolle's theorem will tell us that there exists. Let me use the notation C. So this is actually very commonly used in higher level mathematics. This is just the Greek letter, and it's called C. So there exists a C sitting between C and C1, such that f prime at the point C is going to be equals to 0. Okay, before continuing, let me give a remark over here. So we have obtained the conclusion that f prime of C equals to 0. And in this conclusion, we did not use the formula for f. So for every function that is continuous on the interval and differentiable on the interval, and moreover, with two endpoint values to be the same. So for any such kind of function, we can deduce the fact that f prime of C equals to 0. And this is irrelevant of this formula over here. So as long as the assumption is correct, we must have this. And now let's check if this is possible. So now let's actually look at what f prime of x is. So by f prime of x, so this is going to be equal to 3x squared plus e to the x. Okay, so for this guy over here, we can see easily that since x squared is greater or equals to 0 and e to the x is strictly greater than 0, so this two will imply me that f prime of x is always greater than 0 for every x. So this is actually a contradiction. So there does not exist a C such that f prime of C equals to 0. And this contradicts. So this is contradicting with the conclusion from Rolle's theorem. We are obtaining this contradiction because our assumption is wrong, so there does not exist another root C1 that does not equals to C. All right, so this is basically arguing for uniqueness. So a few remarks over here. So first, we are actually using Rolle's theorem to conclude that the derivative has to take 0 somewhere, and over here we did not use the formula for f. And over here, when we try to obtain the f prime of C of 0 is nowhere. So over here, so the non-existence of this 0 point of the derivatives follows from the formula of f. So the reason we are obtaining these contradicting facts is because our assumption over here is kind of wrong. So that's how we argue the uniqueness of the root over here. So this part over here argue that there exists exactly one root. Okay, so this concludes the arguments for number 20. So let's briefly recap what we have done again. So first, we used the intermediate value theorem in the first step, and then we argue that there exists one root. Then we used the mean value theorem or Rolle's theorem or MVT. So we use the Rolle's theorem to argue that there exists exactly one root. So basically, that's the procedure of arguing such kind of problem. And this procedure will basically be used for all such kind of problems asking for exactly one real root. Okay, let's look at another such kind of example. Let's actually look at number 21. So number 21 is slightly trickier because there is actually a parameter c over here. To make it a little bit easier, let me first solve the following version, namely 21 prime. We would like to show that the equation x cubed minus 15x plus 20 equals to 0. Let's actually try to show this equation has exactly one root in the interval minus 2 to 2. Okay, so how do we deal with this one? Well, the first step is still to use intermediate value theorem. So let's start by setting the function f. So let f be the left-hand side, so namely x cubed minus 15x plus 20. So this is my f of x. So then this is actually a polynomial function. So since f is a polynomial function, so f is continuous and differentiable everywhere. So in particular, it will be continuous and differentiable on minus 2 and 2, but you don't need to actually argue that part. Okay, so now let's actually test the values. So when x equals to minus 2, and let's see what we have. We have got minus 2 to the cube, minus 15 times minus 2 and plus 20. What I will get is minus 8 plus 20, 30. And then plus 20, and the answer will be 50 minus 8 will be 42, and that's greater than 0. And actually, I don't really care what this number is. I can simply say this guy is greater than 0. Okay, so how about f of 2? F of 2 will then be x cubed, 2 cubed minus 15 times 2, and then plus 20. So this will be 8 minus 30 plus 20, that will be 28 minus 30, that will be minus 2, which is going to be less than 0 over here. Okay, so then intermediate value theorem applies to conclude that there exists a c sitting between minus 2 and 2, such that f of c equals to 0. All right, so this concludes the first part that we located one real root for this equation. So IVT argument showing that exists a root. Now let's argue the uniqueness that we have got exactly one root in this interval over here. And the drill is basically the same. So suppose there is another root C1 sitting between minus 2 and 2. So that's such that C1 does not equals to C. So this is our assumption, and we will see that this assumption is wrong. Okay, so what does that tell me? So then f of C1 does not equals to f of C. And moreover, since the function is continuous and differentiable everywhere, so that we can apply Rolle's theorem. So Rolle's theorem will tell me that there exists some C sitting between C1 and C. So in particular, because both C1 and C are inside the interval -2 and 2, so basically the graph looks like -2 and 2, and C1 is inside and C is inside somewhere. So in particular, C is between C1 and C, so that basically tells me that C is also sitting inside -2 and 2. Let me actually say it's actually open interval, -2 and 2. So there is a C sitting in -1, -2, and 2, such that f prime of C equals to 0. So again, this did not involve the formula. So we just assume that we have got such a root, then we conclude that f prime has to take 0 somewhere. And now let's see if that's possible. So let's compute f prime of x. So, but f prime of x equals to 3x squared minus 15. Okay, 3x squared minus 15, what does that tell me? So this is actually going to be a function on 0 to -2 and 2. So it's pretty easy for you to track that on -2 and 2. So you see that x squared is going to be sitting between 0 and 4. So, well, this is quite easy for you to figure out because if you have got x squared over here and x is between -2 and 2, so you should be able to see that the largest possible value we can take is going to be 4, and the smallest possible value will be 0. So we see that x squared will be sitting between 0 and 4. So this will tell me that 3x squared will be sitting between 0 and 12. So 3x squared minus 15 will be sitting between minus 15 and 12 minus 15. Okay, what does that tell me? So so this will tell me that f on the interval -2 and 2, f prime of x will be sitting between -15 to -3. And in particular, my f prime of x will be less or equals to -3. So the largest possible value of f prime of x will be -3, and this guy is strictly less than 0. So what does that tell me? So there does not exist C in -2 and 2 such that f prime of C equals to 0. So this fact is obtained with the formula of f. So this follows from the formula of f. And yeah, this is again a contradiction. Contradicting the conclusion of Rolle's theorem. So basically means this conclusion is wrong, and we obtained this wrong conclusion because we started with the wrong assumption that there is just another root such that C1 does not equals to C. So this way tells me that our assumption is wrong, and therefore we see that there does not exist C1 does not equals to C with f of C1 equals to 0. So this way we see that C is the only root of f of x equals to 0 on -2 and 2. All right, so this is basically the proof. So basically what we did over here is to use Rolle's theorem to argue that there is a uniqueness Okay, so this concludes the discussion to number 21 prime. And now let's handle the original problem, number 21. Okay, so for number 21, we want to show that the equation has at the most one root. And we first need to understand what does it mean for the equation to have at most one root. So at most one root, this basically means the following two cases. The first case, only one root. And the second case is just zero root. So no root at all. So these are the only two cases. So in order to show that the equation has at most one root, it suffices to exclude the case where the equation has more than two roots. So that's all we need to do. And the procedure will be very similar to the second part in the previous problem. And let's actually go over the details. So we want to exclude the case where the equation has more than two roots. Okay, so let's formulate the argument. We start by letting f of x be the left-hand side. So that will be x cubed minus 15x plus c. So then we know that f is continuous and differentiable everywhere because f is a polynomial function. So remember to write this sentence, and you do not need to provide a justification, but writing this sentence will allow you to use the Rolle's theorem afterwards. Okay, so assume x1 and x2 are two numbers in the closed interval such that f of x1 equals to f of x2. And moreover, we could actually assume that x1 and x2, they are not equal to each other. Okay, so then you can apply Rolle's theorem. So this will imply that there is a C sitting between x1 and x2, such that f prime of c equals to 0. So notice that c sitting between x1 and x2, this means c is also sitting between -2 and 2. And now let's actually see if that's possible. So if you look at f prime of x, so you see that, well, f prime of x is precisely the same guy as before. F prime of x equals to 3x squared minus 15. So using the same argument as in the 21 prime part 2, so we see that on -2 to 2, so f prime of x will be less or equals to -3, which will be strictly less than 0. So there does not exist C in -2 and 2. And let me actually get the open interval such that f prime of c equals to 0. So then this is actually contradiction. And this contradiction says our assumption in the beginning over here, so this guy is wrong. So there does not exist x1 does not equals to x2 in -2 to 2. F of x1 equals to f of x2 equals to 0. I think I forgot the equals to 0 over here. Okay, this way we excluded the case where the equation has more than two roots, because it has more than two roots, and in particular, it will have two roots, namely x1 and x2 over here. But from the argument of Rolle's theorem, together with the formula of f prime of x, we see that this assumption is wrong. So we excluded the case where the equation has more than two roots. So the only possible case will be only one root or there's no roots. So which means it's going to be at most one root. All right. So if you want to investigate a little bit, you will find the following facts. So first, so if you choose your C to be between -22 and +22, so then in this case, f of x equals to 0 has exactly one root in the closed interval -2 to 2. On the other hand, if C is greater than 22 or C is strictly less than -22, in this case, f of x equals to 0 has no root in -2 to 2. The first one is pretty easy to argue, but the second one over here requires a little bit work. So basically speaking, the most convenient way to argue this case is to use the fact that f of prime of x will be strictly less than 0. So this will mean that f will be decreasing on -2 and 2. So then if you test it, that f of -2 is less than 0 and f of 2 is also less than 0. So then in this case, well, you will see that the function cannot possibly take 0. So either the graph will be strictly above the x-axis or will be strictly below the x-axis. All right. Okay, so I will leave it to you to figure out more details about these two remarks. And if you're confused, also feel free to ask. All right, let's look at number 22. So for number 22, we want to show the equation x to the 4th plus 4x plus c equals to 0. So this guy has at most 2 real roots. So what does that mean for an equation to have at most 2 real roots? So at most 2 real roots, this means possibly 3 cases. So first case is actually exactly 2 roots. And the second case is exactly 1 root. And the last case is no root at all. Okay, so in order to show that the equation has at most 2 real roots, all we need to do, or in more formal writing, it suffices to show that f cannot have more than 3 roots. Okay, so how do we argue that part? Well, this argument will be similar. So first, let f of x be the left-hand side, x to the 4th plus 4x plus c. So this will be the function. Then, because this guy is a polynomial function, so f is continuous and differentiable everywhere. Okay, so now we want to show that f cannot have more than 3 roots. So let's actually assume that x1 less than x2 and less than x3. So this will be a very convenient choice. Then we'll just assume that these 3 numbers are roots, 3 roots for f of x equals to 0. Okay, so what happens over here? So then first, from f of x1 equals to f of x2, together with the fact that f is continuous and differentiable on the open, respectively on the closed and open interval x1, x2, so then Rolle's theorem will tell me that there exists C1 sitting between x1 and x2, such that f of C1, f prime of C1 equals to 0. Okay, so similarly, on the next interval, x2 to x3, and let's actually do that. Let me just be lazy by copying everything over here. So from the fact that f of x2 equals to f of x3, and Rolle's theorem will tell me that there exists a C2 sitting between x2 and x3, and such that f prime of C2 equals to 0. Clearly, we have C1 to be less than C2, and because C1 is to the left of x2 and C2 is to the right of x2. So C1 is less than C2. So we basically have obtained 2 roots for the function f prime equals to 0. But now let's actually see if that's possible. But f prime of x is going to be, let's compute it using the formula. So f prime of x will be 4x cubed plus 4. And if f prime of x equals to 0, so this will tell me that 4x cubed plus 4 equals to 0. So this means x cubed equals to -1. And you are actually getting only one solution, x equals to -1. So f prime of x equals to 0 has exactly one root. So this will tell me that there does not exist C1 less than C2 such that f of C1, f prime of C1 equals to f prime of C2. All right, so this is basically a contradiction to what we have seen over here. So we have concluded that using the Rolle's theorem that C1 for C1 less than C2, f prime of C1 and f prime of C2 must both be 0. But well, it turns out that f prime of x equals to 0 has exactly only one root, so there does not exist such kind of C1 and C2. So this is contradiction. And we are obtaining this contradiction because our assumption is wrong. We assume that there exists 3 different roots for the same equation over here. And so from here, we see that this assumption is wrong. So, so f cannot have more than 3 roots. Okay, so this will conclude the discussion to number 22. All right, so this kind of problem is actually quite tricky in general. So, okay, so this problem appeared last semester in the 3rd term test, but then we decided not to include such a problem in the term test this semester. However, I will still insist on lecturing these problems in at least the supplementary video, because I think it's helpful for students to have some exposure to the argument by contradiction. This is actually a very, very useful method to prove some mathematical facts in higher level research. So yeah, at least you have seen some argument by contradiction in the calculus course. Now let's actually continue with this additional problem. So this is actually a word problem. It's related to the dynamic understanding towards the mean value theorem. So the problem states as follows: at 10 o'clock 17 minutes a.m., you pass a police car at 55 miles per hour that is stopped at the freeway. So you pass the second police car at 55 miles per hour at 10 o'clock and 53 minutes a.m., which is located 39 miles from the first police car. If the speed limit is 60 miles per hour, can the police cite you for speeding? So in order for the police to cite you for speeding, all he needs to do is to prove at some point your speed is above 60 miles per hour. And this can be achieved using the mean value theorem. So within 53 minus 17 minutes, so this is going to be equals to 36 minutes, and well, 36 minutes equals to 36 divided by 60 hour, which is going to be 0.6 hour. So within 0.6 hour, so you traveled 39 miles. So the average speed equals to 39 divided by 0.6. This is actually divisible. So this will be 13 divided by 0.2. And 13 divided by 0.2, this will tell you it will be 65. So your average speed will be 65, and the unit is mile per hour. So the mean value theorem will tell me that there is 6 times c between 10:17 a.m. and 10:53 a.m. when your instantaneous speed is 65 miles per hour. So the police can cite you for speeding. So that will be the conclusion. Although I seriously wonder whether the police nowadays really understands mean value theorem. So, but at least mathematically, the police has a reason to cite you for speeding. All right, so this concludes the additional problem. Okay, so we are left with number 6 and number 8. And allow me to be lazy not to record these two problems today. So I will just use my older recordings I made last semester.